So I have a new paper up. I just was reading one of the engineering test books, and I remembered I wanted to talk about diathermal and adiabatic walls. Um, Diathermal means heat transfer can happen through the wall, and adiabatic means heat cannot transfer through the wall. And I have here in the abstract, walls that permit the transfer of heat between system and surroundings are diathermal. Walls that do not permit the transfer of heat between system and surroundings are adiabatic, meaning they're good insulators, thermal insulators. Young stars' walls are diathermal and shine. As their outer walls, the photosphere directly transfer heat to outer space, which acts as a tremendous eternal heat sink. As the stars age, the ionized hydrogen combines with itself, forming hydrogen gas, which has an extremely high thermal heat capacity and makes the star's outer walls adiabatic. It basically means the star, when it's hot, bright, and young, the outer photosphere is thermally conductive. It's diathermal. The heat can transfer to outer space from inside the star to outside. And then over time, as the star collapses and contracts, that ion, the hydrogen ion, combines with itself, making hydrogen gas, and creates a thick blanket of material around the collapsing star, and it continues forming the planet in its interior. So that thick thermal blanket is post-brown dwarf stages, and it's thermally insulating, meaning that increases the age of the star considerably. It can't lose heat as fast. Think of those thermal blankets, those thermal survival blankets, where it radiates the heat back onto you. But there's more to that, what meets the eye. So I have young stars transfer their heat to outer space. This means the outer walls are diathermal. And we can directly observe this heat transfer just by standing outside on a sunny day. We know the sun is transferring heat from its interior outside through its walls, its photosphere, out into outer space, because we can feel the heat of the sun. We can get sunburn from the UV radiation. It heats up the atmosphere of the Earth, and the water vapor traps heat because that's the largest, greenhouse gas. And that's what keeps the atmosphere warm. If Jupiter was in place of the sun, there would be no strong radiant heat. Hi, Celeste. If Jupiter was in place of the sun, Jupiter wouldn't be able to heat up the Earth. It's definitely hot enough inside of Jupiter, but the amount of heat available versus the sun, as the sun is a much younger star, plus the fact that the heat is internalized and trapped by the Jupiter's very, very thick hydrogen blanket atmosphere, and the heat can't escape as easily, which means it's basically like a planet oven. It's cooling and collapsing and heating up the interior, forming the planet's interior, and that hydrogen gas prevents that heat from escaping as the planet is forming in its interior. It's a very time-consuming process. It follows from the principle of heat evolution. I link that to this paper as well. Of course, this paper isn't up on Vixray. I just posted it. Jupiter's heat is internalized. It is far older than the sun and has taken almost all of its ionized hydrogen and combined it into hydrogen gas, which acts as a massive thermal blanket. The massive thermal blanket allows for the formation of the embryonic metal-cored young planet in its interior. Stellar evolution is planet formation, for those who are new to this theory. The non-thermally insulated stars cool and collapse, and that hydrogen ion combines together, making hydrogen gas, which acts as a thermal blanket. And eventually that thermal blanket is removed, exposing the planet that's done forming in its interior. And just to give a few examples, what a diathermal wall is a wall, it's solid, or could be solid, or could be made of plasma, which I think the sun is, a diathermal plasmatic wall, the photosphere is. Like pots and pans and copper pots and pans. You can stick the copper pot on top of a stove and heat up food with it. The heat goes right through the copper, basically. It's a good thermal heat conductor. Um, Adiabatic walls, like double pane windows. For instance, up north, I know you have double or even triple pane windows, and it isn't just the glass isn't just there like in Florida windows where it doesn't have any air inside. If you make a double pane window or triple pane window, there's a little air gap in between the two glass panes, and that air is what allows the heat to be trapped. It doesn't allow for heat transfer through the glass as easy because there's air there. Air is a very good thermal insulator. And hydrogen gas is even better than the air we have in our atmosphere, the nitrogen and the oxygen gas. If we could fill double pane windows probably with hydrogen gas, they would be more thermally insulating, but I don't think it's wise to do that because hydrogen is extremely explosive. We know that from the Hindenburg crash. The Germans made the Hindenburg, filled it up with hydrogen gas, thinking everything was hunky-dory, and then some accident happened and the whole thing just blew up. So we learned our lesson with hydrogen gas. But it's a very good thermal insulator at lower temperatures. For instance, Jupiter is extremely cold when it's outside. Neptune, Saturn, Uranus, they're really, really cold. That hydrogen, it can't combust because it's too cold. It's not in its combustible state. It's very stable, and it's an excellent thermal insulator. It's adiabatic. So basically, those are different stages of those thick thermal blankets being removed. Neptune would be much older than Jupiter and Saturn. Neptune would be down here. And eventually that thermal blanket is almost completely removed, as in the case of the Earth, where just the nitrogen and oxygen are left over, which are also good insulators, but not as good as hydrogen gas in large amounts. All right, you guys, I think that sums up this talk. It's very important to understand that young stars, they transfer heat into outer space, and they continue transferring heat into outer space. There's nothing stopping them from transferring heat into outer space. Outer space is an excellent way to remove all the heat from a body, because you just radiate, and outer space just doesn't get any hotter. It's like an amazing heat sink. All right, today is June 1st, 2020, and when this paper comes up, I will link it to the bottom. Take it easy, y'all.